Hey guys, welcome back. So in this final tutorial of the fundamentals of machine learning, we're going to understand the challenges of machine learning. Now if I quickly present it. So till now we finished the intro, types of ML systems, and also looked at a very simple linear regression example. All right, now let's look at some of the challenges. So, for instance, insufficient quantity of training data, non-representative training data, poor quality data, and last but not the least, overfitting and underfitting. Do keep in mind these are not the only challenges. There are few more, but I've only put those that makes more sense as of now, and depending on the use case and what problem we are solving, of course there are always some challenges, but as a general, if we have to generalize just the challenges or the problems that we'll face during building a model or just doing machine learning, these are the these are the ones that we'll be facing. So let's take a look at it. Now of course it's in the Jupyter Notebook itself. All right. Now, yeah. So challenges in machine learning. So the first and foremost is insufficient quantity of training data. As you might have already understood, like I was talking in the first tutorial, that we often, find ourselves not having enough data, or we often find ourselves not having the um, proper quantity of data, or the type of data we get is not enough. So that is one of the major issue. I know now ML has exploded because of the vast availability of data. However, those data are not fine tuned, or are not in the way that we or the machine learning model expects it to be, right? So the first one is insufficient quantity of training data. As you can, pretty much understand, it is pretty much self-explanatory, in the sense that here we talk about an example. So let me just read that. For a toddler to learn what an apple is, all it takes is for you to point to an apple and say, "Hey, that's an apple," right? And possibly doing this quite sometimes, not a whole lot of times, but a few times until the toddler learns. Once he's learned it, now he or she can easily recognize apples of all sorts and colors and shapes, right? Uh, However, ML systems are not quite there yet. So just because I showed like one or two examples of apple and told that, hey, this is an apple, this is an apple, machine learning model cannot generalize it very well, because of if we don't, especially if we don't give enough quantity of data to the machine learning model so that it can generalize on different use cases, right? So machine learning is quite not there yet. It takes a lot of data for most machine learning algorithms to work properly. Even for simple problems, you would typically need thousands of examples. And for complex problems such as image or speech recognition, you may even need millions of examples, right? So that is one challenge, that in the sense that we need not just the data, but in the way the machine learning algorithms need it to be, right? I hope that makes sense. Next is the non-representative training data. Now again, this is pretty much self-explanatory. What this means is, if you are training your machine learning model on something that is not completely representing what you want the model to do, right? So this is often something that we find ourselves doing a lot, maybe knowingly or even unknowingly, right? If we don't have enough domain knowledge, then this is certainly something that we will end up doing, just because we don't know enough, or we don't have enough domain knowledge. For instance, when we trained the GDP and life satisfaction, we did not have all the countries, right? We only had about 29 or so countries. Um, so now, if we take a look at different countries that were missing, Brazil, Mexico, Czech Republic, and all those, and when you consider these countries and all as well, and then create the linear regression model, right? They don't perform the same. So here you can see the solid line is the new model, what you get, and the dotted line is the old model. So you see how it has also tried to fit the new line to Norway, Switzerland, Luxembourg. Uh, it is try to fit that line closely to the different countries. Now, if you were to take the old model and then predict on Norway's GDP and Switzerland and all that stuff, or all those countries, the model is definitely bound to produce incorrect results. And we also understood that with this graph or with this scatter plot, that as the GDP increases, the life satisfaction increases, right? But however, that is not the actual case. In some cases, if you see, they are, just because the GDP increase, not always the life satisfaction increases. There are a lot of other parameters and attributes that um, you know uh, dictate life satisfaction. However, it is not fair to just conclude based on the GDP alone, right? Uh, so these are the things that we would have to take care of. Of course, this we won't learn in just a day, but repetitively doing the same thing over and over again, and we'll know what the problems are, and maybe if data is an issue or the non-representative training data is an issue, maybe we might realize that, hey, this data is not exactly what or what we want the model to do, right? Moving on. So poor quality of data. Again, this is pretty much self-explanatory. Now, if we have data, that is missing or full of errors or outliers, right, it makes it harder for the machine learning algorithm or system to generalize and identify the patterns, right? um, so it might perform well on the training data, but on the test it is definitely not going to perform well. So here what we suggest is it is often well worth effort to spend time cleaning up your training data. And truth be told, most of the data scientists spend a significant part of their time just doing that. So trying to clean up the unrelevant or irrelevant data and data that is missing or not really needed, right? So what the suggestion is, if sometimes instances are clearly outliers. What do I mean by outliers? Outliers are someone or something that does not just generally fit into the data. So they just keep doing their own self. So for example, I know it's a pretty wild one, but for an example, if I had to say, now let's say you're studying 8th or 9th or maybe even 10th class, uh, but if your friend starts studying 11th class syllabus or 12th class syllabus, right? So he or she is definitely an outlier, because the general trend is to study what your syllabus is, right? But if your friend, he or she starts studying, what the syllabus is not, maybe 12th standard mathematics, right? Um, then that person is definitely an outlier. So that's what outliers mean. So they are completely out of the hurdle, so they do their own thing, right? So what we do, if there are some instances that are clearly outliers, it may help to simply discard them or try to fix these errors manually. Try to understand why that outlier, or why did we even get that outlier in the first place, right? That makes more sense. And in some instances, if there are features missing, for example, now when we are talking about an example where you're writing a blog and you want to understand the kind of people who visit it, right? And you ask them a survey which consists of few personal details, maybe even their age. Well, some might input their age and some might not input their age, right? It's totally up to them. You cannot force them to apply or input their age, right? So in those cases, what would you do? Well, some has their age inputted and some have their age not inputted. So what do you want to do in those case scenarios, right? So that again falls under the poor quality of data, where it is inconsistent with the rest of the data. So what you could do is either ignore them or fill in the missing values. Now, how would you fill in the missing values? Maybe you can take the median, right? median, mean, average, whatever you want to do, you could figure it out and fill in those missing values, or just ignore them altogether. Or here's another wild one. You could train one model with that feature and train another model without that feature and see how it performs with and without those features, and see really if that feature is any indicative of what the target variable or is, right? So that is, couple of things, one of the couple of things that you could do. And again, irrelevant features. Yeah, as the saying goes, garbage in, garbage out, right? So if you're giving your model some features that really has nothing to do with the target variable, right? So it makes no sense to even keep those features as the training set in the training sample itself. So it's better to discard those kind of features that that for sure that it does not add any value or bring value to this model to predict our target variable. So here your system will only be capable of learning if the training data contains enough relevant features and not too many irrelevant ones, like I said again. And the critical part, a critical part of success of ML project is coming up with a good set of features to train on. Yes, this is of course a pretty critical one, in the sense that if you have the domain knowledge and you understand the data completely, and then you have some insight, you do some data analysis and have some insight as to what factors actually affect the target variable that you want to predict, right? Versus what factors actually don't affect. So those things you can figure it out, and this process is also called as feature engineering. You will hear this term a lot in statistical machine learning, or even in just deep learning occasionally, right? So feature engineering is a very uh, pretty critical process, right? So feature selection is selecting the most useful features to train on amongst the existing features. Not all, do keep in mind, not all the data you collect is relevant for your model, right? And feature extraction, combining existing features to produce a more useful one, right? So those things, and then creating new features by gathering new data. So what you could do is these things. You can do feature selection, feature extraction, and creating new features by gathering new data. All right, moving on. We have overfitting on the training data and underfitting on the training data. So this is a pretty crucial one that we usually always, not always, but usually we are bound to run into this issue. Now let's understand what overfitting is. Now let's understand with an example. Say you're visiting a foreign country and the taxi driver rips you off. What it means when it says rips you off is that the taxi drivers demands more than what is actually the bill to go from place A to place B, right? So what you would do generally is you might generalize this and say that all the taxi drivers in that countries are they rip you off and they overcharge you, right? That is called as overgeneralizing. So this is something we humans do often, and unfortunately machines can also fall into the same trap, right? So yeah, if we are not careful. Now how do we make sure we are careful? We One of the step is to make sure that we provide ample amount of data for the model to work with again, and then we optimize, we do all the pre-processing steps, all the errors that we might that we have discussed here. So making sure we do all of these and keep our due diligence, taking care that the model does not just by hurt, right? So that is what overfitting is. So in machine learning, this is called overfitting. It means that the model performs well on the training data, but usually performs terrible or generally does not perform well on the test or validation. So what that means is it cannot generalize well. So given a new set of sample, it will fail to generalize on the new on the new set of sample actually. So that is what overfitting is, right? So it's like a model by hurts everything. So now for an example, if I have to say, um, Now, if you were to buy her, if I asked you to buy her 2 pages of the book, you can easily do that, right? Versus if I asked you to buy her the entire chapter or the lesson, it's quite difficult. So instead, what you would do is, well, by heart is one option, but you would rather see how you can, you try to understand that the chapter and try to generalize, right? So if asked a new question on that particular topic, you can extrapolate and try to see where this, what logic could be applied from that chapter and try to solve the problem. So that is a good generalization mechanism, and that's exactly what we want the machine learning model to do. We want it to generalize pretty well. However, if we only give less data, what it will do is that it's easier for the machine learning model to just by heart it, because the data is less, and maybe even if we throw in some irrelevant features that makes no sense to the model, it will just ignore it, and it might not ignore it, it will consider it and just perform very miserable on the test when we're trying to predict. So these places are the ones that we, or these pitfalls are the ones that we absolutely want to avoid. Now moving on, we have the underfitting the training data. Now you might have already guessed, it's the exact opposite of overfitting. Now underfitting, is the opposite of overfitting. It occurs when your model is too simple to learn. Now here we created a model, right? Now this is a pretty simple model. Now if you talk about neural networks, if we just add one neuron, right, or maybe one unit, one hidden unit in the input itself, right? It cannot. It's not even going to understand what the data is. So it is very much underfitted. So these are the. I mean, this scenario is also not where we want to be. Definitely, this will yield in your predictions to be inaccurate. Yes, that's about it. So in a nutshell, there are definitely challenges to machine learning approach. The first and foremost is insufficient quantity of training data. Then comes the non-representative training data, and then we have poor quality of data, irrelevant features, overfitting and underfitting on the training data. So I hope you guys got some insight as to what are the common pitfalls and what are the general challenges that any machine learning engineer, when he or she is just starting out, will usually fall into. So we don't want to be here, but sometimes it's inevitable because we might not have relevant data, or we might not have enough data altogether, right? And we might end up overfitting the model again. So this is what we need to take care of, and we always have to spend more time in these aspects than developing the model, right? So you saw that creating the model and predicting is just like a matter of two line code, whereas preparing the data set even for a small problem like this, because we did not have the data set as we wanted, we discarded unnecessary features and only kept the GDP per capita and life satisfaction, and the country, of course, as the index. So even for a problem that is so simple, we'd have to do so much pre-processing. Now you could imagine if you're trying to solve some major problem, right? Maybe some natural language processing or image classification. You could only imagine how much pre-processing we'll have to do. But don't get overwhelmed. Don't get scared. There are brilliant minds who have already figured out, and there are definitely some techniques that we can always follow no matter what we are doing, right? If it's a machine learning or deep learning project, then there are a few pipelines that we can always follow, and we might see good response in the model. That is the good accuracy of the model. All right, so I'm going to stop here. Now if you guys have any question, please feel free to ask. But apart from that, yes, so we have finished the fundamentals of machine learning. If we quickly take a look at the agenda. So we finished the fundamentals of machine learning, the intro to ML types, linear regression example, and challenges. Now next comes the supervised techniques, and data visualization, analysis and visualization, unsupervised techniques, and all that good stuff. So stay tuned. Until then, take care. Bye bye.